Hello, my name is Ari Rubenstein, and today I'll be talking about how we can measure the resilience of different autonomous controllers to misthrust events, and we'll be demonstrating this on an example Mars to Earth trajectory. This is part of an ongoing collaboration between the Astrodynamics and Space Research Lab at the University of Alabama and NASA's Jet Propulsion Laboratory. In this image, this nice GIF on the screen, you can see a spacecraft trajectory in green departing Mars and heading to Earth. On the left, you can see the neural network optimal controller that's actually controlling the trajectory. It takes in the state information, and you can see all the little neurons active in the network. And as different state information comes in, you can see their activation rates changing and thinking and deciding what the control output should be. In this talk, I want to go over three main questions. Why do we want deep space navigational autonomy? What are some methods for achieving navigational autonomy? And then how do we measure the autonomous performance of these methods with respect to misthrust events? And in the end, we're going to combine this all and explore these different methods on a sample Mars to Earth trajectory. With the advent of deep space CubeSats like Marco and the coming NEA Scout, the number of spacecraft in our deep space fleet is set to grow. While these spacecraft will be great for science and exploration, they will place an increasing strain on the limited bandwidth of the deep space network and on the GNC engineers ourselves. To meet this challenge, we'll either need expansive infrastructure updates to communication infrastructure like the DSN, or major increases in the number of GNC engineers, or improvements in spacecraft autonomy. And in NASA's 2020 technology taxonomy, they have an entire high level dedicated to autonomous systems. These new deep space explorers are hoping to use high efficiency propulsion techniques like electric propulsion or solar sailing. Unfortunately, these propulsion methods require thrusting arcs that are much longer than more traditional propulsion methods. Instead of thrusting for seconds to minutes for a transfer, the thrusting arcs are now weeks to months long. Unfortunately, 60% of spacecraft enter safe mode every 200 days, and a propulsion system goes inactive during one of these safe modes. So if a safe mode overlaps with a thrusting arc, this is called a misthrust event. And even a 10-day misthrust event can delay arrival by 200 days, or even cause the complete loss of a mission. Now, we don't just have to worry about one misthrust event. In this plot, we can see the number of misthrust events, as well as their probability of occurrence for a 1.1-year trajectory. If we look at the probability of one or two misthrust events, we can see that it's actually greater than the probability of no misthrust events. What's more is the cumulative probability of two or more misthrust events is greater than 50%. So even this short 1.1-year trajectory, the question will be, how will we deal with all the misthrust events that will occur? Now, back in 2018, Travis Imkin and a few others at NASA's Jet Propulsion Laboratory looked at 240 beyond-Earth safe mode events, and they found that the time between misthrust events and the duration of these misthrust events both followed Weibull distributions. And we can see the parameters in this table down here. Now, the Weibull distribution has two parameters, a scale, which is just a scalar you multiply it by in the beginning, and a shape, which tells you how the evolution of the likelihood changes over time. So a shape greater than 1 means the instantaneous likelihood of an event happening increases over time, while a shape less than 1 means the instantaneous likelihood of that event happening decreases over time. Now, when dealing with misthrust events, two schools of thought arise. There's the first, which is resilience, and that attempts to design resilient trajectories prior to a misthrust event occurring. And there are many different ways to do this. The main approach that's used is to either provide some sort of suboptimal quantity, like additional propellant mass, additional schedule slip dates, and additional duty margins, which can then be consumed after a missed-thrust event to aid in reconvergence. The second method is called a ghost swarm trajectory, which is when you design a nominal trajectory and you perturb it a bunch, and you simulate missed-thrust events throughout it, and you adjust that nominal trajectory until you're able to reconverge the trajectories after each missed-thrust event. And then finally, the newest method is called expected thrust fraction, and that's where you directly embed the stochastic nature of missed-thrust events into the optimal control problem itself. The other approach is autonomy, where the spacecraft attempts to correct trajectories on its own once a missed-thrust event has occurred. And the big question is, how do we design autonomous trajectories that are resilient to missed-thrust events? So, and from a high-level overview, all autonomous approaches come down to one item: solving the underlying Hamilton-Jacobi-Bellman equation that corresponds to the optimal control problem. Unfortunately, the Hamilton-Jacobi-Bellman equation is often a nonlinear, non-smooth partial differential equation, which is very hard to solve globally. So instead, we find that it's easy to solve it for a specific instance and then just locally approximate the solution to the Hamilton-Jacobi-Bellman equation, either as a function of time or as a function of state. And in both cases, the solution is some control history. So the two approaches we're going to be using that approximate the solution as a function of time is the run-the-clock approach, which parameterizes the controller as a function of time since the start of the mission, and a stop-the-clock approach, which parameterizes the controller as a function of time since the start of the mission minus any time lost from missed-thrust events. Now, when we approximate as a function of state, we're going to use two separate neural networks. The first is a neural network optimal controller, which is a deep neural network using several layers. And the second one is a shallow radial basis function network that uses radial basis neurons as the basis of the network. So when I talk about neural networks, I'm not going to go into detail on them, but to give you a high-level overview, think of them as general-purpose function approximators, like a Fourier series or a polynomial fit to some data. You have some inputs, which are the spacecraft's state in this case, and you have some outputs, which are the corresponding optimal action. And inside you feed the inputs into these things called neurons, and these are just some nonlinear function. Now, in a polynomial series, they would have a function of the form x to the n plus c1, x to the n plus c2, x to the n minus 1, ... And before we could use that polynomial series, we'd have to find out what each of these coefficients correspond to. And in the neural network world, that is, we have to do the same step of finding the weights and biases. And this is called training your neural network. And there are different methods for training your neural network, but we're going to use supervised learning, which is where we have a trained set of spacecraft states, and we've already computed the optimal actions from that state, and we provide the state action pairs to the neural network in the training process. So once we have our different autonomous controllers, we're then going to need to measure how resilient each of these trajectories are to missed-thrust events. And the way we do this is by simulating 1,000 trajectories with multiple missed-thrust events. And we go over this more in the paper, but we're simulating those missed-thrust events in accordance to the statistics found by Travis Imkin and others. And then once we've simulated those trajectories with missed-thrust events where the controller can autonomously control the trajectory through it, we then measure at the closest state, using the 2 norm, the success criteria, whether it arrives within some pre-specified arrival tolerance, the lateness, which is how early or how far after the nominal arrival is this closest state, and then the optimality, which measures the percent difference between the optimal cost function and the cost function as calculated using our autonomous controllers. Now, this allows us to get a quantitative sense of how well our controllers are performing and how sensitive our controllers are to misthrust events. But in order to understand about sensitivity to a single misthrust event, we're actually going to turn to a graphical method. And this figure is adapted from an earlier work we've submitted called Neural Network Optimal Control in Astrodynamics, Applications to the Misthrust Problem. And in this, we can see we've simulated a single misthrust event, and we've varied that single misthrust event based on the start of that misthrust event and on the duration of it. So, for example, this point right here, we simulated a misthrust event 50 days along into the trajectory, and that misthrust event has a 2-day duration. We then allowed the controller to control the trajectory after that misthrust event, and saw that it arrived within our arrival tolerances, and so we marked that as a success with a blue dot. However, if we take that same misthrust event, but extend the duration out to 8 days, we can see that the neural network optimal controller can no longer drive the spacecraft into the success criteria, and now we mark it as a failure with a red X. Maintaining an 8-day duration misthrust event, but having it occur at the 200th day after departure, we can see we've once again succeeded in arriving within our pre-specified arrival tolerance. And we can also see in some of the plots a nice clear boundary between the success regions and the failure regions. So we have an idea of how sensitive our trajectory is at different points along the trajectory. Something that this plot does not show well is the probability of different numbers of misthrust events. So 70% of misthrust events are 3 days or less, as demarcated by this green line. So what that's saying is 70% of misthrust events are somewhere in this region, where you can see that we have a perfect success rate here. So now that we've talked about what our metrics are for measuring autonomous performance resilience to misthrust events, let's try it out in an example case, a sample Mars to Earth trajectory. We're going to have Mars and Earth in circular planar orbits. There's going to be 2 body dynamics in polar coordinates, and we're going to have a low thrust propulsion system that produces 1.3 newtons and a fixed initial mass of about 3,300 kilograms. We're going to be trying to minimize the control over the trajectory, which is to basically say we are maximizing delivered mass with a fixed initial mass, and we have a fixed time of flight of 1.1 years. Our spacecraft has 2 control parameters, U, which is its thrust fraction between 0 and 1, and then beta, which is the in-plane control angle. Now, if we take the deterministic case, we can see our spacecraft trajectory departs from Mars and goes inwards before arriving at Earth. And this is the nominal deterministic solution. Now, if we look at the deterministic optimal control solution from a control perspective, we can see that the in-plane control angle stays mainly bounded around pi, and that the thrust fraction that's bounded between 0 and 1 is mainly, there are 2 bang-on regions and 2 bang-off regions, which correspond well to mass optimal control, which is the controller, so this is the type of controller we would expect for the cost function we have. So now let's look at how sensitive different optimal autonomous control methods are as a function of time. And so this case, we can see the run the clock performance and the stop the clock performance. And you'll notice that in the run the clock performance, these failure stalactites line up rather well with the 2 bang-on portions of the thruster. And that tells us that the run the clock portion is very sensitive when the thruster is on and not very sensitive when the thruster is off, which is more or less what we'd expect. What's more is that the stop the clock portion is much more sensitive for a longer duration, but at lower duration lengths is actually a little bit less sensitive than the run the clock controller. If we now move on to sensitivity as a function of state, we can once again see that the failure stalactites in both the radial basis function and neural network optimal controller, again, line up with the bang-on portions of the trajectory. What's less apparent is that in the neural network optimal controller, there are these speckled regions where the neural network optimal controller cannot arrive within the tolerance and has a failure even though it's within a region where it's surrounded by other successes. And we see this occurring in various places. So it's just interesting to note. So if we put all of the different 4 autonomous methods we're testing here, so radial basis function, run the clock, stop the clock, and neural network optimal controller, we can also see something more interesting, which is that this entire region, from about 350 days to the end to arrival, all trajectories are successful, no matter the number or duration of misthrust events. And that's because at that point, the spacecraft, even if it has a misthrust event, has thrusted for most of its trajectory and can now coast into arrival, even if there is a misthrust event. And another big takeaway from all of this is that the neural network optimal controller is, in general, less sensitive than the run the clock controller. But once again, we have those speckled regions, which means that the controller is less predictable. So when deciding between an autonomous controller, you may have to decide between one that performs better, is less sensitive to misthrust events, but is less predictable where it will be sensitive to misthrust events. And then one final point about these sensitivity regions is that so far we've looked at a binary success criteria. Either the trajectory was successful or it wasn't. Instead, we can plot the log of the minimum missed distance at the closest approach. And that's what we do on the right. And you can see on the color bar, anything below this red line is a success, while anything above it is a failure. And you can see the different shapes emerging from the different controller methods. So now that we've looked at them qualitatively, let's look at them quantitatively. And we can see that for a success rate, run the clock performs about 70% successful, stop the clock's about 50% successful, neural network optimal controller is about 80% successful, and radial basis function is almost 100% successful. So we can see that the approximation as a function of state is much more successful than approximation as a function of time for success rate. Now this changes when we deal with the percent difference in optimality, where a lower value is better. And the run the clock and stop the clock, so our controllers as a function of time, are now the better of the two metrics because they are very small percent differences, while the approximations as a function of state have much larger percent differences in optimality. And in lateness, we have more of a mixed bag, with sometimes the state doing better, sometimes the state doing much worse. So, in conclusion, we've identified metrics and figures to compare autonomous responses to misthrust events, and we've shown that state-based controllers have greater success rates but fall short on optimality. And in the future, we want to incorporate misthrust event resilient trajectories into the controller and explore the effects of arrival tolerances. Any questions?